So now we want to turn our attention to the second of our three steps in our AC to DC conversion, which is filtering. And so here we're just going to consider quote-unquote brute force filtering, which is essentially just placing a capacitor in parallel with our load resistor. So capacitor in parallel with our RL. So of course what that's going to look like, we have some circuit, whether that be our full wave bridge rectifier, our half wave bridge rectifier, or our center tapped, and we're just going to come in here with our RL, and in parallel with that we're going to place some filter capacitor C. So this would be our RL, our C, and this is still defined as our V out. And so what is that doing to our circuit? Well, let me first sort of sketch what we're looking at in terms of our input waveform. So we've said before our input waveform maybe looks something like this. So we have the sinusoidal wave, and we have our period. This is T over 2. This is T, so this is our input. And now what our output would look like if we did not have our filter capacitor. Come over here. So without our filter capacitor, let's do that in blue. So we'd have something that looks like this. So let's say this was a full wave rectifier. So let me just come up here and say we had a full wave rectifier circuit, and we threw on this filter capacitor. So then we wouldn't have any gap, we'd just go straight into, try to do that a little bit better. That should be the same size as the other wave, of course, and so on. And so let's say this blue is with no filter capacitor. Okay, so then we add this filter capacitor, and essentially what the capacitor is going to be doing is it's charging up whenever current is flowing through the resistor, and then whenever it is off, or basically when the voltage drops below that peak value that the capacitor is charged to, the capacitor is going to be discharging through the resistor. So let's use a different color here. Let's do orange. And so let's say we came in sort of in the middle of this cycle. So our capacitor has been charging and discharging. So at this instance, it is discharging, and then it reaches a point where the output, which is this blue curve, is getting large enough such that it's larger than what the voltage on the capacitor is. So our capacitor is going to begin charging along with this curve. We then reach this peak value. So now our capacitor voltage is still larger. Our sort of charging voltage has gone away. It's trending towards the other direction. So we're switching between, for instance, maybe this positive half cycle towards our negative. And so what is happening then is our capacitor begins discharging through our resistor. That's going to continue until we get to this point here, at which point our capacitor begins charging again. And so that process, of course, is just going to repeat as we go through here. So a couple key things to note then. So let me label our plot a little better. So this is our V out. Let's say this is our V in. And in both of these, we have time on our horizontal. So a couple important things that we can label. So one is related to how much this voltage here is changing. So if we look at sort of the minimum value our voltage is ever at, and this peak value our voltage is at, well, the difference between those two is what we're calling our ripple voltage. And so of course you can see why we call that the ripple voltage. It kind of looks like ripples in water, or sort of like waves. So that value would be our ripple voltage. So just sort of as an example, maybe if this value down here was at 11.5 and this peak value up here was at 12.0, then we would have a ripple voltage of 0.5 volts, which is a relatively large ripple voltage. But again, we have to keep in mind it depends on the application. If we're talking about for high gain amplifiers or for digital circuitry, that would be much too high. Now for lights or motors or any type of heating, that is most likely going to be an acceptable value of ripple voltage. The other important thing that we can label here in this circuit is our frequency, related to our frequency. So if we pick a point, so let's say this point, we can say that occurs at this time, and we look for the point where that's sort of repeated, so that would be over here. So the difference between these 2 points would be 1 over our ripple frequency, because again, remember, our period is just 1 over frequency, so 1 over our ripple frequency. And let me draw that maybe a little clearer here. Let's do 1 over f ripple. And so for this case, for our full wave rectifier, we can see that our frequency for our input wave would have been from here to here, because again, this would have been our positive half cycle and our negative half cycle. So we can see our ripple frequency is half of our input frequency, as we said in our previous video. So now what we want to do is we want to have an equation that can relate our V ripple, our F ripple, and the size of this capacitor, as well as the value of our current. So we're going to go back to sort of some basic equations. So let's make an assumption that we're drawing a constant current in our DC output, so from our power supply. So constant current draw. And so what that means is we can write that dV dt is equal to negative I dC over C. And so this is going to be when we're discharging. And so what we notice is that this is essentially just our capacitor IV equation. So remember, we have I equals C dV dt, so we've just rearranged that a little bit with the C on the other side. And of course we have the negative because our capacitor is discharging, so our voltage is decreasing. What we can also consider, another equation that we should be familiar with for a simple RC circuit, is just the natural response equation. So we can say our natural response of our RC circuit is going to be V of t is equal to our initial voltage, V naught, times e to the negative t over tau, where tau is equal to RC, which is our time constant. And if we wanted to be really general, what we could write is we could write this as R equivalent and C equivalent, but in this case, we're just considering one load resistor and one capacitor, so that would just be RL and C for this case. But in general, we could say REQ and CEQ. Okay, so how can we play around with these equations to get an expression that relates ripple voltage, ripple frequency, capacitance, and current? Well, it would be a little difficult, but we can make it easier by making another assumption. So what we're going to assume is we're going to assume that this ripple period, which is indicated here between these purple lines, is small enough such that we can approximate this decrease as a linear decrease. So really, looking at this equation, we know that that's not true. We know it's going to be an exponential decrease. But maybe if we just take a small enough piece of that, if we sort of zoom in far enough, we would see that it's approximately linear. So if we make that assumption, we can sort of simplify things. So let me just go ahead and put that in words here. So we're assuming that our ripple period, which is just 1 over our ripple frequency, is sufficiently small and basically what I'm saying is so that our exponential decrease can be approximated as a linear decrease. So exponential decrease can be approximated as linear. Okay, so what that means then is we know if we're talking about a linear decrease, it's going to be a lot easier to discuss this dV dt. So we could say our dV dt, well, dV is just how much our voltage is changing along that highlighted line in our graph there, and our dt is how much our time is changing. So what we can do then is we can relate that over time, our dV is going to be equal to our ripple voltage. So it's going to be the ripple. Our dt is going to be equal to 1 over our ripple frequency, so this is equal to our ripple period. So now if we want to be technical, of course, our dV is going to be negative because we're talking about a drop. So if we plug that into this previous equation here, what we can see, and we can solve for v ripple, we'll have negative v ripple divided by the dt, which I can just flip that up here to the numerator. So f ripple is equal to negative I dc divided by c, and for our two negative signs will cancel out, and we'll see that our v ripple is equal to I dc divided by c times our f ripple. So that would be our equation relating our v ripple and our f ripple. And so really what I should have instead of equals, I should have this as approximately, because again, remember we're making this assumption that our ripple period is sufficiently small so that exponential decrease can be approximated as a linear decrease. So one thing to note when you're using this equation is we have to be very careful about this f ripple, because for certain types of circuits, for instance our half-wave rectifier, we know that Fn was equal to f ripple. But in other cases, for instance in our full wave bridge rectifier, we know that our f ripple is equal to twice our input frequency. So something to keep in mind as you're applying this equation. So what we're going to look at in all of our subsequent videos is we're going to focus on our third step, which is our regulation. And so we're going to come back and we're going to start by saying why is our regulation even necessary? Why can't we just use filtering? And then from there we're going to look at different types of regulators.